CLI and a cross-platform IDE for C and C++. Download now.
Thanks for joining me this afternoon, and I hope you've enjoyed the conference so far this week. So we're going to spend a little time today talking about legacy code, ways you can maybe look at improving it, and also ways of looking at sharing code that might come along with that. I'm Roth Michaels. I'm a principal software engineer at Native Instruments, which is a group of companies that have merged together recently in the audio industry, made up of Native Instruments, Isotope, Plugin Alliance, and Brainworks. I mentioned this just because I come from the Isotope part of the family originally, and so some of these stories are coming more from that Isotope perspective versus necessarily other parts of the group. And just a little bit of a background on what we do. We make software for music production, both software and hardware. And this is for digital audio, for mixing and mastering records, producing beats, DJing, post-production for film and television. And there's just some context that some of the examples we'll talk about are kind of from this digital audio industry, but you don't need to know anything about audio or DSP to understand the examples from our stories today. And all of the stories we're going to look at are from mostly all actually real experiences that have gone into production. Others are, a couple of them are actually just some prototypes that were production ready, but we haven't needed to ship those features yet. And just a reminder that these are kind of an experience report, and I'm sharing some opinions and discussing about ways to make pragmatic choices to help you deliver customer value. But none of these are hard and set rules, and some things might even seem a little controversial, but useful at certain points. These stories are going to be both about improving code as well as ways that you could kind of make it more shareable and reusable, perhaps within your company, your code base. And I'm going to be sharing some tips for kind of other resources on these topics that will come up along the way. And before we get started, something I often like to bring up at the start of my talks is that, the stories I have to share today are from my experiences working with my code base and my company, but I'm sure everyone here listening today has had interesting things they've learned, and we'll have a more vibrant community the more people come out and give conference talks. So if you've never given a conference talk before, I'd encourage you to think about it. I'm sure you have something from your experiences and learnings that would be interesting to share with others. And also, lightning talks at conferences are really a great way to get into this, because it's a lot lower pressure to maybe try to put together 5 minutes than a whole hour. And that's how I got my talk speaking at conferences. But let's get back to the topic at hand, legacy code. And I think kind of one of the main things I want to talk about is really one of the strategies for dealing with legacy code is really how to make sure the new code is better and your code base is slowly evolving in this direction. This is a kind of a theme of there's been part of a number of the talks I've given over the past few years. My first talk I gave at CPPCon was about taking a part of our legacy UI libraries, and instead of actually replacing that legacy code, putting a nice new layer on top, so at least the new code we wrote was easier to use. So I don't know if anyone is in the Discord at the moment. If you want to hop into the Adventures with Legacy Codebases Tales of Incremental Improvement channel, for if anyone wants to have a little audience participation. But I was kind of curious, before I show my list of bullet points, if anyone wanted to type in, what do they think legacy code means? I see someone's typing, so we'll have at least a little participation. Thank you. Code not written by me. Yeah, that is a good one. Although sometimes I feel like legacy code is also code written by me. C code masquerading into C++. Yeah, the C masquerading of C++ is an interesting one, and could definitely be an interesting cultural change when someone comes to it from a team. If they were, maybe working in a situation where they were writing pure C most of the time, at first they might not see why, some macro shenanigans or other stuff that might seem okay in C, that we should really do it a nice C++ way. code that works. That is also actually a big theme that we'll be hitting on today. I actually don't have this on my list, but like that is a big topic, is code that works. Not extensible, no tests. Yes, I think we're seeing some of the classic answers. I'm gonna see there's a couple more responses coming in. Code I would not give to an intern. Oh, that's a neat one. Oh, mixed language code. Fortran, C, C++, C Sharp, all mixed together. Luckily, I don't have too much to deal with that. It's mostly C++. We have a little bit of objective C++ in there. Poorly documented for sure. So the list I had is no tests, just lots of kind of verbose code. Code is very old, not written by me. The authors might be gone, so you can't ask them questions about it. A code base that might have gone through many C++ standards, so you might have had code written before move semantics in parts of it. Code could have new and old styles of writing or new and old paradigms that you're using. And a really interesting one is bad decisions from the past that once made sense. Often we might have some class or poorly designed what we feel is a poorly designed piece of infrastructure in our code base that we're stuck with dealing with, might give us some overhead. But it actually turns out there was a real business reason that our colleagues 10, 20 years ago might have written that code. But as the product of the business evolved, those decisions from 10 or 20 years ago might not make sense, or maybe some code possibly written by a less skilled engineering org. The three companies that I was talking about that we merged together all have over 20-year code bases. And when those were started as founder businesses with college students coming out, just the average level of experience at the company was lower when it was a brand new company versus a 25-year-old company. I just seen some more fun stuff in the chat for stuff, auto pointer and some crying about that. But yeah, I'm sure we can. I'm kind of curious to hear, just catch up later on what other ideas people are throwing in there. Also, I just wanted to mention, as I was going to suggest some other resources, I have not actually checked out this book in much detail or the tools myself, but I've had a colleague who has recommended this to me, who has used it in the past. This book, Code as a Crime Scene, and some tools that help you kind of do an analysis of your legacy code. So this is on my to-do list for more investigations on this topic. So I wanted to suggest this to all of you. Oh, legacy version control systems. That's an interesting one, actually, because while we are using Git day to day, we did shut down an old server that had our ancient CVS and other stuff on there that we wanted to back up for posterity for old products. Oh, consistently inconsistent. Yeah, that's what we see also as we talk about new paradigms coming up throughout the code base. And another part of this is, often when we talk about legacy, we also talk about a lot of stuff. Usually, this was from a talk I gave a few years ago internally about our code base, and I had titled the slide "How Big is the Universe?" referring to, at the time I gave this talk, if we were to look at all the code to build all the products we're currently shipping, how much code is that? And I know lines of code is a silly measure, but I was actually mostly talking about making the point of how much we're leveraging open source, because you can see there's an order of magnitude more pieces of open source lines than product lines. But you see, we do have about 2 million lines of code between shared code and product code that we're dealing with. And some of that might have tests, some of it might not. As someone pointed out, the legacy stuff that's there, it works and has been doing great for us. And this is just from the isotope part of the business. So if we look at this group of companies together, all with over 20 years of code, we have a lot of interesting stuff like this. And we've had a lot of chats about, ways we've tried and failed to improve things, and also sharing code between 25-year-old C++ code bases is pretty interesting. And we'll get into that more later. So before we start talking about some of the improvement techniques and other things, I wanted to share a little cautionary tale. And this actually goes to the point about someone brought up about legacy code being code that works. And if you're going to make updates to that legacy code, maybe that becomes new code, but it's no longer code that works. So we had a story where we had a number of different ways that we were setting up Python projects internally, a couple different ways that we were deploying them to our internal PyPy server. And that was not ideal. And this was a case where we decided, well, it'd be better to have one standard way to manage Python projects. So developers who aren't experts in this don't have the mental overhead of needing to manage 3 different systems. So we decided we're going to adopt Poetry, and we had some templates for a PyProject TOML file for our Python projects. If you don't know what that is, it's basically just, the project config for this Poetry packaging system. But what came along with this default template for new projects, when that was being used to adapt an existing project, that brought in new linters, new type checking rules. And to pass those things, that required code changes to be able to actually pass those tests that we were not running before. Even though, as someone said, this legacy code, it worked, the tools were doing their job, but they needed some changes to pass these linter tests. And there was a number of times where developers were trying to do good things to modernize one of these tools to add more type checking or make some changes to appease the linters in our new project templates. And quite often actually led to the first release of the tool built with the new template having some bug or breaking change that was not realized. Another variation of this, at one point, there was a team that had set a goal to increase test coverage in some of their Python tooling. And part of that journey involved refactoring to make the code more testable. And this is a term that is often thrown around, meaning I'm moving some code around. But really, hopefully, when we say refactoring, we mean changing the code without changing behavior. But when you're doing a refactoring like that to make your code more testable, you're taking the risk that actually you do change behavior by accident, and you're making this you're making changes to be able to add tests. But if you don't actually need to change that code, maybe it doesn't actually need the tests yet. I'm not attributing this quote because I forget both the number mentioned and exactly who said it, and I think it was a little bit of a joke, but a large percentage of your code base likely might get rewritten over the next 5 years. And so adding tests to some legacy pieces that you don't know you're necessarily needing to change, is introducing risk. Because if you know you'll never change that piece of that subsystem, maybe it doesn't need new test coverage. Or if you know you're going to rewrite part of it, maybe that's when you add some regression tests just to make sure you're not going to screw up. Because anytime we're making a change, even just reshaping some code to add the tests, we're all human, and there's the chance that we could make some mistakes. So there's 2 sci-fi video clips I'm often sharing with my colleagues that relate to this story. One from 2001: A Space Odyssey.
I hope the 2 of you are not concerned about this.
Oh, I'm not, Al.
Are you quite sure?
Yeah, I'd like to ask you a question, though.
Of course.
How would you account for this discrepancy between you and the Twin 9000?
Well, I don't think there is any question about it. It can only be attributable to human error. This sort of thing has cropped up before, and it has always been due to human error.
And yes, this is something I'm seeing a lot often when, problems show up in our code base. It's due to human error and we made some mistake. And the biggest way you can avoid introducing human error is don't disturb a working system unless you actually have a real customer or business need to make changes there. Refactoring just for, improvement on its own probably takes more risks than delivers value to the customer. And the other thing I like to share often, specifically, in situations where, a developer is forced to make a bunch of changes to adopt a new linter in an existing library. I share this clip from Metropolis where you see this person kind of working away, trying to kind of this human being in service of the machines. And that's something I think we need to make sure we're avoiding doing ourselves. Just because the linter in our default template says, you must make these changes, if it's not worth us putting the extra energy and calories into making those changes if it's not going to deliver clear value to the user or the business. And so, the kind of takeaway here with this Python library story is don't change code without user or business value, and just adding tests might not actually be delivering that. That being said, there's always exceptions. Old code can sometimes slow us down. And so even though that might not directly have business value. There might be times where we know we're being hurt or slowed down by old code and we do need to change it, but just improvement for the sake, for the sake of, making everything consistent or one style is, a losing battle over a 20-year or 25-year-old code base. So let's talk about some successful strategies for slowly evolving and improving your code base. One of them is involving style guides, and in C++, clang-format is your tool for that. And my recommendations for this are always provide a clang-format file. Even if you don't have automatic ways of applying that formatting or checking in CI, it will at least make it much easier for other people to come in and from other teams and potentially collaborate on your legacy system if they at least have a format file that's going to let them write code in the way that you and your team are, without needing to really learn that if they're coming into a new area of the code base. And so if you have this format file in place, that will take care of formatting. And then when someone's making changes to the legacy system, you don't need to be distracted by formatting things, and your code review can really focus on the actual changes you're making. And then the other thing that we have found that was very successful is I know some teams, when they adopt clang-format, oh yes, we'll get David, thank you for bringing this up. That can be a real situation. So and if you're not in the Discord, Dave was bringing up that clang-format and CI and locally, you can run into issues where between versions of Clang, unfortunately, the defaults of clang-format change, and then they can format things differently for you depending how you things have set up in your file. But I can make a suggestion regarding that. But some teams like to, when they adopt clang-format, reformat their entire code base. Yes, you have your Git authors or Git blame will have a format commit in there. That's one viable strategy, but another one that we found works quite well is to not worry about reformatting all code, but just make sure new code is formatted with clang-format. So we made some Git hooks that will take the lines output from the Git diff or Git and create a patch from that, and then only apply the formatting to the actual code changes. And then that way, and we have this as a pre-commit hook so that basically anytime anyone's committing code, those change lines are always having their formatting applied. And then we verify this in CI by essentially running that hook again. And theoretically, there should be no, if you ran it locally, there should be no changes in CI when you run that hook. As David pointed out, with differences between Clang versions, you can run into situations where developers might have a different version than is in CI or a different developer's machine. The way we handle that is we actually build our own clang-format and clang-tidy. We'll get into that more later, why we have to build those. But whether you're building your own or have your canonical binary, we have a repo of tools that we're kind of expected to have available. And so our formatting tools are always pulling a specific binary for the platform of clang-format to use so that local developers and CI, if they follow our setup instructions, will have that same version. And so the next thing I'd like to point out about improving your legacy code is with static analysis. And there's some great tools in Clang, and now some of these sanitizers are also in Visual Studio and GCC as well. But my experience is this mostly with Clang. And I mostly have experience with ASAN, UBSAN, and TSAN, which are address sanitizer, undefined behavior sanitizer, and thread sanitizer specifically. And they're very great tools for finding issues and undefined behavior in your code base. I go into much more detail about this and kind of how we adopted these tools and made behavior changes at our company to avoid writing more undefined behavior. So if you're interested, you could check out that talk for a more deep dive on this topic. And before I give you some of my specific tips and tricks on this, I just wanted to share this XKCD comic that I think is worthy to think about when it comes to undefined behavior. So I'll just give you a moment to take a look at that. So maybe a little bit extreme. It's not everyone our field is bad at we do what we do. We actually try really hard. And oh yes, actually, thank you for someone pointing this out in the chat. That was actually a mistake I made in the slides. The next one with clang-tidy is static analysis. The sanitizers are actually a runtime analysis, even though some of this happens at compile time with there are some checks where UBSAN will actually insert like UB happened here instrumentation, I believe, in the code. But thank you for who brought this up in the Discord, that actually these are checks that run at runtime. And in the moment, I'll talk about kind of rollout process with this stuff. But you're right. This was accidentally mislabeled slide for, thank you for pointing that out. But C++ is a dangerous and hard language to use, so we have to leverage our tools to make this work well. So, with this, as someone, thank you for pointing out, this slide should say, no one called me on this the last time I gave a version of this talk, that this is improving with runtime analysis. And we had great success with an incremental rollout of ASAN and UBSAN. It took a long time, but it helped us get a lot of coverage on our code base. In general, there really aren't any like issues with false positives we've found. There's one trick later I'll mention regarding vtables and dynamic libraries that might need working around. But in general, it's been a super stable and useful tool. Where we did not have as great success was using thread sanitizer, which we didn't run on our test framework. So a lot of our tests are running in a single threaded environment. So we did full manual product testing with thread sanitizer. And in that situation, there were some false positives, and we had kind of a lot of QAs spinning wheels, filing bugs that were false positives, and we need to work around those. So thread sanitizer is a little bit trickier to roll out. And one of the other sad things is not all of the Clang sanitizers are compatible with each other. So if you're running ASAN or UBSAN, you can't run thread sanitizer at the same time. How we roll this out is writing tests and trying to increase our test coverage. And so that we're starting out by rolling out these sanitizers at different levels of what is sometimes called as the testing pyramid. And so usually you want your foundation, a first level of testing, and probably where there's kind of the most tests are your unit tests on kind of individual functions or components. Then you might have some higher level integration tests, and then some end-to-end tests. And we found for rolling out sanitizers, it's useful to go from the bottom to the top of this testing pyramid, as usually you'll be kind of testing more and more of the system that way. So for us, making audio software and plugins, what this means is for our testing pyramid is we have unit tests are kind of what you'd expect. We're using Google Test mostly, and unit tests pretty straightforward. Then for the integration test level, we have a number of digital signal processing regression tests that we run, basically to make sure that anytime we're making changes, the actual audio output isn't something that humans will perceive as being different as before the change. And then we use a full end-to-end tests. We have some tools to test our products using the VST3 API and format, which is one of the many audio dynamic library formats that are available. And so we looked at rolling this out. If you kind of imagine a nicely shaped code base like this, if you imagine this is a product where that top box is your high-level product code, your bottom boxes might be some vocabulary types, and you have various libraries that are kind of built on those low-level components. We started at the very lowest level, and just at our most lowest level library, turned on UBSAN and ASAN on those tests, and then you get that passing green, and then over time you add more and more and more of these libraries to get more and more coverage. And this is something, every incremental improvement you can make is going to make your code base better. You don't have to solve all undefined behavior at once in a 25-year-old code base. That's going to be quite challenging. But as you add more libraries up the stack, you get more confidence. And then once we got not all of our library code running with UBSAN and ASAN, but once we had a lot of it, we were able to, at that point, add the top level product code unit tests also running with ASAN and UBSAN. And then once the low level components and then the highest level unit tests were running with these sanitizers, that gave us pretty good confidence. And then slowly we continued to roll this out over the whole code base. Now all of our unit tests are running with the sanitizers enabled. And we've now also begun our integration regression tests and the end-to-end tests also beginning to enable those sanitizers. But every time you take a library and enable the sanitizers, usually you'll find something that needs to be fixed. And thanks for someone in the chat. Just, I'm also just interested in following along with some of the Discord discussion. Yeah, regarding refactoring, this is always a big help in code review if you split up the refactoring and the actual change at least into 2 commits, if not actual pull requests. And speaking of refactoring, let's talk about changing legacy APIs. And should you do it? In our code base, we have a number of different ways of dealing with something like, do we have a value or not, that we would normally reach for standard optional. But our code base precedes standard optional. So we had our own version of this checked value. It had some issues with implicit conversions. It's maybe not the nicest thing to use. Then once it was available, we started using boost optional in some places in our code base. Then in some libraries where we wanted to start adopting standard optional, we used a type def for optional, which was standard experimental optional on some platforms and boost optional on others. And then in those libraries, we only used the subset that overlapped. And then we actually started using standard optional. And all these different types will behave slightly differently. And before we talk about what we decided to do about all those optional types, another XKCD for you to enjoy for a moment. Yeah, as a Emacs user, I also kind of find that very funny. And the conclusion I would have about this is ideally you want no breaking changes, because if you're going to be changing interfaces where you have to switch from one of these optional types to another type, that's going to inhibit other people adopting the changes you've made. And there might be some exceptions to make no breaking changes, and some is maybe use small libraries, because one situation you don't want to get yourself into is, imagine that you have a library of foundational code and you wanted to get rid of all of these different kinds of optional values and say, okay, we're going to use standard optional everywhere, which that is a noble goal to have. But if you make that change and bring that along with a bunch of other unrelated things all in one library. Imagine you have some SIMD code related to ARM, and so that might be important for like a transition to Apple Silicon. And what if, to get those new Apple Silicon support changes in your library, I also have to take the breaking change you made to all of your vocabulary types? So if you're going to, be breaking APIs, if you have smaller, more self-contained libraries, that's potentially one way you could avoid getting to situations where people are forced to refactor their code because one thing changed, even though they're updating your library for a completely different reason. Or even better, provide a transition plan. And I'll provide a few resources to you that I encourage you to look at regarding ways you can change code over time without making breaking changes. Usually this involves two-phase refactoring, making a new API, deprecating old ones, and then eventually having some way to move to the new API. So C++ at a live ahead language is a great talk I enjoy by Titus Winters that, kind of got me on the bandwagon of all changes can be potentially breaking changes, and that using the latest version of all your dependencies has a lot of benefits for detecting, breakages. When we actually switched with some of our teams to using specific commits in our code base of dependencies to always building with the latest of all our internal dependencies, we discover defects much faster because every team then kind of becomes testers. And if you break some other team, they'll find out real quickly, let you know, and revert and make you revert your change. And if everyone's using the latest version of dependencies, they find out you broke them that day instead of weeks later when they finally update. Maintaining refactoring impact of high-level design features is another talk that I think shows a number of nice examples of what types of things could actually require breaking changes. And then also, the best way to deal with breaking changes is actually make a refactoring tool and you can do this with clang-tidy to actually automatically transform the code base. So if you've deprecated a function, clients can run some tooling and automatically bring you over to the new version. Kristen Shaker has one of my favorite talks I've seen that shows some really great techniques, and this is a lot easier to do than I found it used to be now that there's some tooling in Compiler Explorer for this. And this is something that I think a lot of C++ developers would benefit from learning about and leveraging more. And then one other kind of interesting talk on this topic is thinking about, live ahead and versioning. There's a talk from Bloomberg, lessons learned from packaging 10,000 C++ projects, and for Brett Brown and Daniel Russo. And this has some interesting things to think about regarding dependencies and versioning that you might want to check out. And just sharing kind of one simple thought that kind of relates to that. That I learned from the John Lakos book, Large Scale C++ Process and Architecture, is sometimes we might, not want to repeat ourselves, but sometimes copying some code might actually be the best way to improve and make new stuff without breaking your legacy client. So imagine you have tool A that depends on some library, my component, or that could just be a class or a function within some library. And tool B comes along and it wants to use my component. But during the development of tool B, we discover that we actually have to change my component a little bit. But that's going to risk a regression in tool A. And sometimes if you have a working legacy thing, especially maybe if it doesn't have great test coverage, that risk might be too high of breaking tool A. And sometimes it might just be worth it. And we might not like, repeating ourselves, but to actually just make a copy of my component, call it my component 2 or whatever, and make the changes there so that you don't actually have to risk that regression. Okay, and as thank you for someone pointing out earlier, our previous section was mostly talking about runtime analysis. Now we're truly into the static analysis section, and also how to handle deprecations, also using clang-tidy. Because this is something that we are using so that when we say we don't make breaking changes, we deprecate old APIs, and then we have a system in place where it is a build failure to ever use one of our deprecated APIs. So they'll no longer pollute the code base, and eventually, as more code gets rewritten, less code removes those. Eventually, the deprecated APIs can go away. So the way we do this is we use a tool that's comes along with clang-tidy called clang-tidy diff that allows you to only run the clang-tidy checks on lines that you've changed between 2 commits. So we do this on any pull request. We clang-tidy diff between that and the main branch to run the main clang-tidy checks. And I mentioned earlier that we build our own clang-tidy because we've written a few internal checks about some APIs we don't want to use anymore, or other things like this that are specific to our code base. And make your own checks requires compiling your own version of clang-tidy. A couple things that you might run into if you're dealing with this is that the compilation database that you might be generating might not work entirely right for clang-tidy. Some things we had to do is replace our pre-compiled headers with the real header in the compilation database, and also instruct the compilation database to treat all headers as Objective C++, because we had some headers that were Objective C++, and just being .h, this was not detected out of the box. And then the way we use clang-tidy to prevent any use of deprecations is that we normally in our normal build configuration, we have warnings as errors turned on and a few left just as warnings. So we leave the deprecation warnings just as warnings. And then we can use, when we run clang-tidy, we then make the deprecation warning a warning as error. So that way we can deprecate something. It's not going to break any existing code, but any new code is going to fail CI if it uses that. And, we can verify this in CI. And then also, if you're going to do this technique, you're going to need to probably also have a way to strategically disable the deprecation check in CI, because you can run into a circular situation where if in one pull request you deprecate an API and need to call it from the new API, or sometimes even deprecating classes itself can make this loop where changes to the deprecated code are showing up and causing a deprecation failure. So you can run these like adding a new deprecation can sometimes make the thing itself fail the deprecation check with clang-tidy. I see some interesting chat about line keeping per line checks, and so like I'd like to circle back on that when we get to the Q&A at the end. But one thing you might be wondering is, well, if we're just deprecating old APIs and not getting rid of them, like how will they ever get out of our code base? Well, eventually you'll have less and less uses over time. And also the other way you can do this is by developing a culture on your teams where people really like deleting code. And one of the ways we've done this internally is we have a Slack channel called the Red Diff Appreciation Society, where we get to brag about pull requests where all we do is delete code, and everyone cheers for you. We have special emojis that we put on, and this is just a really kind of fun way to build community and have an attitude that we like deleting code more than we like writing it. And so even though things might just be deprecated at first, eventually someone will see there's not that many uses and get the bragging rights of actually deleting code. So now that we've talked about, some of the issues of, legacy code bases and trying to improve things, let's talk about sharing code a little bit, because this is, something I've been dealing with a lot the last 4 or so years since we merged these 3 companies, is how to deal with taking advantage of all the tech we have across these companies, but it's 20 to 25 years of legacy C++. The biggest thing to worry about is the risk and the desire to standardize. We might want to do this because we've built, we're all companies in the same industry, so we have a lot of similar things. We have lots of similar but also unique DSP algorithms we might want to share, probably hundreds of individual signal processing algorithms. We probably have about 7 different UI technologies across the 3 companies and various eras of products, at least 4 installer technologies, and I could keep going on. And there's the desire to well, what if we had only one UI framework? Well, some of you might have seen this comic about standards. But yeah, so unifying this stuff can be a big project. And now, even though it might be nice to take our code base and have a mix of maybe some green code as some library stuff and some product code, and then we're all mixing from different places, really, as you find these components, having a big project to make, here's going to be our new standard thing is, going to be challenging. But ideally, as you're finding a reusable component to put together to make a product, you're actually finding that out of existing practice. And so one of my colleagues, instead of standardizing, what he proposed is we discover our hidden gems. So look at we all have code that we don't like in our code base, legacy stuff like we were talking about in the first part of the talk. But when it comes to actually making reusable components and sharing within your teams, even if you're not dealing with a merger situation like I was, And you have to look at like, well, what are the pieces of technology that we really would like to use and that would help us, build better products for our users, and then turn those and figure out how to make those into reusable components. And one nice tool for this, there's a link here you could check out for more information. If you've not heard of it, it's called a tech radar. And it's a way of like for both techniques, tools, languages, libraries, ways of assessing kind of how they exist within your software ecosystem that you're building with. Are they for mainstream use? Is the deprecated thing we should never use anymore? New technology we're looking into? And this is a really kind of a good way to get a map of, where's your legacy technologies? Where's the new things you want to use? What things should be reused between projects? What things shouldn't? So that's one thing I recommend you check out. And before we get into some of my sharing techniques and examples, I just want to kind of get some more audience feedback in the Discord about what you might think some challenges that might become with sharing legacy C++ code. Okay, I do see a typing ... Oh, different string types. Yes, this is definitely part of the talk. No one wants to touch it. We'll see what else shows up in there, but I'll show you the list I put together for my slide. Different build systems is going to be one. Possibly different teams or different code bases are using different language standards. You could be using different versions of the same third-party libraries. Precompiled headers can give you some trickiness because often precompiled and like a prefix header are conflated. So you might actually have situations where the precompiled header is not there, or often if you're using a precompiled header that brings in a bunch of stuff, that's the first thing you include in every CPP file, you're very likely to write header files that might not compile on their own. Weird legacy vocabulary types, like I said, are checked value instead of standard optional, or we have a string type as well. Code bases might be bringing things into the global namespace that you don't have to type std, or putting our own types and polluting the global namespace, which is not great for sharing. Different error handling strategies. Some might be using things like optionals and expected. Other code bases might be using exceptions, and different coding styles, whether that's paradigms or formatting styles. And build flags is another tricky one for sure. So as I said before, the biggest thing that will help someone be comfortable helping and trying to share your legacy code bases is please provide a Clang format file. But I'm going to quickly go through a few different strategies that have worked for us. One is dynamic library sharing, and this is probably the easiest one. So this first came up using a dynamic library format we already had in place for regression testing called testable DSP, and I'll tell you a little bit more about that in a moment. But essentially, we had two, very legacy products: Ozone, this mastering software from Isotope you see up top, and Tractor, a DJ program from Native Instruments that you see on the bottom. And we wanted to take this maximizer DSP you see on the top and make that a feature in Tractor. But how were we going to deal with all of these legacy build issues that we did before? Well, luckily, we had this dynamic library format that was basically a very simple plugin format that we'd use for regression testing. So we might build a library, which you may see at top, and then maybe a gold version that we keep. That's our we know we want to sound like this. And we set the params the same on both of them, pass audio through, and compare for regression tests. Similarly, we also do it with like two copies of the same library to make sure it behaves deterministically. And this has some simple APIs for C APIs for creating and destroying the DSP. And that gives you, and this is, there's more to the API, but you get some API that looks kind of like this for interacting with the DSP code under test, allowing you to set parameters and a process function for actually processing the audio. And what that gives us is this firewall where we can keep all of the monsters and dark secrets of our legacy code bases separate, hidden behind the DLL boundary. And this means we don't need to share build systems. We don't need to worry about unifying our third-party libraries, ODR violations, the PCH infection. And this actually turned out to be a really nice pattern where we're able to take, through this testable DSP interface, make adapters where we can take an element, which might be what we call some DSP code in the Isotope code base, and turn it into an IDDSP core in the NI code base using this DLL boundary, but then wrapping it up in nice wrappers so that you could just use, DSP from one company's code base and the other with across this dynamic library boundary. One kind of gotcha I wanted to mention when you're using, throwing C++ types across dynamic library boundaries is that even though technically it is the same type, the type info might be different if you don't expose the type Clang with by visibility default or DLL export on MSVC. And you also can run into UBSAN failures where it will actually see these things as different types across the DLL boundary if you don't do this. So that's the dynamic library sharing. The next technique is actual source code sharing. This is the most exciting one. And we had some success with this. If you got some stuff that can be header only, that's probably the easiest for source code sharing. So this one didn't actually go into production, but we had a machine learning system for building models of guitar amplifiers. And the machine learning output would actually generate a C++ class with certain constants that would then use eigen to which is a matrix math library to actually do the ML calculations. And eigen was already a library we were using. So we were able to actually just very easily make the output of this tool be header only, and then write our own template that would take this header output and turn it into the APIs expected by our DSP libraries. And so this was very successful and something that we are ready to use when we actually need it for a user feature. And then some other useful example is, as we did the merger, we wanted to actually be able to provide licensing and authorization with a unified system. And so we were going to adopt the native instruments authorization library in our Brainworks and Isotope plugins. And this was part of a monolithic, shared libraries repo they had. So we split out the library from the monolithic repo, talked about custom string types or path types. We rewrote it so all the custom vocabulary types were using standard library types, and we aligned on a small set of third-party libraries that all companies could easily adopt that this library would use. So we needed Boost, Base64, and Loma and JSON. And as far as build systems, we just put the build scripts and build system files for all build systems used at the company in the repo. And yeah, we have to repeat ourselves, but that works. Next one, it's kind of a variation of source code sharing, is copy paste sharing. And sometimes if the code is simple enough, this is really all you should do. And yes, people don't like to repeat themselves, but this is sometimes the easiest. In this example, we had a legacy and loved isotope distortion plugin called Trash that would really kind of mess up your sound. And we wanted to take some of those processing effects and make them available in Guitar Rig, this guitar effects program by Native Instruments. And instead of we could have gone that dynamic library route I shared before, because we do have dynamic libraries of all this DSP, but the code they wanted was all simple, pure functions. That was one digital sample in, one digital sample out, simple transfer functions. And so since they were all simple, pure functions, involved no other types than floats, it was easier just to copy and paste them into this other code base than actually worry about our dynamic library trick for sharing signal processing code. And the last one maybe is a little scary. We wanted to share a user instrumentation and analytics library with one of the other teams and code bases. And we settled on sharing pre-built static libraries, which might sound a bit like a wild, crazy project. So why we decided to do this is we had this library that at lower levels had management of the opt-in to the analytics from the user ID management, local caching of events if they're offline, and the actual event dispatch mechanisms. And we had a high-level reactive programming system that we would use for actually sending the events out from the software. The team that was going to adopt this library didn't need that top level of reactive programming, but they found a point in the library that they wanted to integrate with. So we looked into seeing, well, can we do source code sharing or dynamic library sharing for this? And source code sharing, we were blocked on, as someone brought up earlier, the multiple string classes. So we have this utility for interacting with Apple's plists or the registry on Windows or other file system configurations on Linux we call config file. And it uses our legacy string class, which in modern days is actually just standard string under the hood with a different API, but it exists for legacy reasons. And that was going to take us too long for the time we had for this project to fix that problem. So we didn't want to infect their code base with all this other stuff. So source code sharing was out for now. Dynamic library sharing, we know it works. We had a good experience with this. We decided on an abstract API for the virtual interface, but this would require them making some changes to their installer technology to be able to deliver this dynamic library. And that was an investment we had to trade off. And since the long-term goal was source code sharing, we decided to do the hack and just actually pre-build static libraries, which did run into a few issues. You know, depending on your build system, it might not actually do anything if you tell it to build a static library. You might actually need to build some linkable target to make it actually build the rest of the dependencies. So we had to have a dummy dynamic library target to just in some of the build systems to get the libraries to build. We turned off LTO out of paranoia, thinking that would be too complex to manage pre-building the libraries and sending them over. We ran into some flags issues. So on Mac OS, they were actually using a different version of Xcode. So we had to send this no Objective-C message send selector stubs flag, which then also, due to build system reasons, we had to pass unused arguments flag. Don't worry about why. And then on Windows, we had to make sure we agreed on the iterator debug levels, whether we're using the static or dynamic runtime or the multi-threaded DLL. And there were a few other flag dances we had to do to make a version of the static libraries that would actually work with their system. So yes, it was painful. But at the end of the day, it worked. And we were able to, get this in the project while in the background still working on fixing the challenges to eventually move to source sharing. And actually, we're there at the moment, new releases are actually going to be built, compiling sources and not doing this shared library thing quite soon. So in summary, focus on new code. You don't have to, or you're not going to be able to fix everything at once. And you want to incrementally adopt things. Incrementally adopting clang-format is useful. Incrementally adopting sanitizers for runtime analysis. And incrementally adopting clang-tidy is something I'd recommend. And I said that was a summary, but we have a little bit of bonus content. So I gave a version of this talk previously at CPPCon. And then when I got back, I was going to be working on that problem I just discussed, moving that static library sharing to source code sharing. And I realized, wait a minute, I'm going to be changing too much legacy code in this approach. And I'm not even taking the advice I just took in this talk. And so we should probably look at a new approach and if that could actually go easier for us. So again, looking at this problem, we have this abstraction over the user default system on Mac OS, the Windows registry, and file system configurations on Linux. And that API is full of our capital S string, which is in the global namespace and is our legacy string class that we really don't want to use in new code. So that's the problem to address here. So this is a simplified version of what this config file class might look like with our old string API. And we prefer it to be something like this with string view. And we were planning to actually just rewrite a new version of this for, the analytics library, any other new code we're sharing to use instead of the old one using our string class. But when one of the developers started off on this project I had proposed, he discovered there's a lot of complications. So there's an internal implementation detail on the Mac OS side called this function read string. Don't worry about what it does, but notice all these orange types are types that are in vocabulary types unique to our code base. And we have a few other types. The CF type ref is a Mac OS type. And basically our string implementation has some magic utilities for interacting with the core foundation strings of the Mac OS system. And there was a lot of risk in changing this stuff. And this was just one function. There's a lot more complications behind the scenes to interact with all these systems on Mac OS, Windows, and Linux. And there was just there was test coverage, but we weren't confident it was enough coverage. And even if there was enough test, it was still going to be a lot of manual work to rewrite all that code for all three platforms. So instead, we decided, you know what? as someone else said, this legacy code is code that we know it works, and we've been using it successfully for over a decade. I haven't checked when it actually came into the code base, but instead we should just actually make the version 2 a API wrapper, and it actually directly calls every function on version 1, and version 1 is an internal implementation detail and others. We just protect others from including our special string class. And if you notice, this config file class has all virtual methods because we mock it in some place for tests. So our wrapper that we write, we could just write some unit tests to make sure that we're actually correctly calling the internal mock version. And the source code sharing is unblocked. So thank you very much, everyone. That's all I have for you today. I'll pop over to GatherTown and also scroll through the Discord, and we can chat some more over there. Thank you very much.